Hello, class. In topic 2.3, exponential functions, you will learn the key characteristics of an exponential function, including the general form, the difference between growth and decay, and the domain and range of these type of functions. Now, in calculus from algebra 1 to calculus, the functions that we studied are linear, polynomial, and exponential. So let's review the prior, linear and polynomial. A linear function is a function that makes it where the graph of the function makes a straight line. That's the equation of the form of y equals mx plus b, or in function notation, f of x is equal to mx plus b, where m, which is the slope of the line, that's calculated by getting the rise of our function and dividing it by the run of our function. y2 minus y1 over x2 minus x1, the change in the y terms divided by the change in the x coordinates. And b, well, that is going to be your y-intercept. Now, the line has an upward slant if the slope of the line is positive, so it moves upwards like this. But if the slope of the line, again, the change in the y over the change in the x is a negative number, then the line will be slanted downwards from left to right. And wherever we cross the y-axis, that's going to be the number that we're adding again to the slope times for every value of x. So m times x. So if we cross to the y-axis at 6, then this number would be 6. If we cross the y-axis at -7, then this number right here would be -7. Now, a polynomial function is a function in the form of f of x is equal to a times x to the n power, or a sub n times x to the n power, plus a n minus 1 times x to the n minus 1, and so on, until I get to our a sub 1 times x to the first power, to our linear term, and then a sub 0, which is our constant. Now, a couple things about these functions right here. Well, these functions, again, are examples of polynomials. The number of times a function is going to curve, all right, and change direction correlates again to this value right here. So if this number is 2, where the value of n is going to be greater than or equal to 2. If this value is the lowest possible number, 2, then this thing is only going to curve one time and change direction only one time, because 2 minus 1 is 1. So that's the number of times it's going to curve. Okay, so it's going to change direction one time. So it's decrease and then increase. If it's to the third power, then it's going to change directions at least 2 times. 3 minus 1 is 2. Okay, at most 2 times. So it can go up, it can go down, and then come back up. This is, again, what x to the third power would look like if we had more terms. Since this one only has the first term of x to the third, it doesn't look like it goes down and comes back up again. It looks like it just becomes horizontal and then continues moving up. But it does have that overall shape to it. Now, the direction that the ends, the right ends go, correlate again to what this value is right here. Recall that if this number is positive, then the right end is going to point again upwards. But if that number had to be negative, then the right end would be pointing downwards. If this number, again, is negative. Now, the left side correlates to the exponent. If this exponent is an even number like 2 or 4 or 6, then the left side is going to match the same direction that the right side is moving. So if this is a negative number, the right side will be going down. And if this number right here is an even number, whether that even number is 2, 4, 6, or 8, the left side will also be going down as well. Now, for your odd degrees, if this number right here is an odd number, 3, 5, 7, and so on, then the left side moves in the opposite direction of whatever the right side is going to be. So, like in this example, in this situation, this value of a would have to be a positive number in order for this to go to the right, and this number would have to be an odd number, 3, 5, or 7, or any odd number bigger than that, in order for the left side to go downwards. Now, if this number was negative, then the right side will go down and the left side will go up assuming again that this number is going to be an odd number. Okay, so there, just a very quick review of both linear and quadratic functions. Okay, let's move on to the next page and let's talk about an exponential function now. Now, first of all, the general form of an exponential function is the form of a times b to the power of x, where the value of a is going to be any number but 0. Or here, a cannot equal to 0, and the value of b has to be a positive number with the exception of 1. Okay, so any positive number not equal to 1. Now, a represents your y-intercept. It represents your initial amount, the amount that we're starting off with. And b represents the base of the exponential formula, or we tie it again to a geometric sequence as the common ratio. So these exponential functions behave exactly like a geometric sequence, with the exception that these things are continuous, they're connected, and they have a common ratio. Now, there's two functions that we're going to be focusing about: exponential growth and exponential decay. An exponential growth function is a function that is always increasing. Okay, so it's going to increase. An exponential growth obviously increases. As you see right here, this graph is increasing from left to right. The formula for an exponential growth function is f of x is equal to a times the value of b to the power x, okay, to this value, where the value of a and the value of b again are going to be positive numbers. And more importantly, this value of x up here is positive. This is going to result in an exponential growth function. For these type of functions that are growing exponentially, the value of a, this again is your initial value. This represents again your y-intercept. So the graph is always going to cross the y-axis at this point right here, labeled 0a. Now, the b value again is your common ratio. This value is going to determine how much again the graph is going to move up. Now, for this specific one, since this function is always increasing, that means that there is never going to be a relative extrema, no local extrema at all. It does not switch directions. Because it's always going up. It's going to start again at the base, or in this case again at this value, and it's going to keep moving upwards. And important information here is that this value of a, the initial value, is going to be again the y-intercept. And from this y-intercept, this point is going to go up again at a rate equivalent to b. So if I want to figure out what the next point is right here, I would just simply multiply b again an x number of times. So I want to figure out where the y value is when x is equal to 1. Then this point right here would be the product of a times b to the first power. Now, since this graph is moving upwards, then the concavity of this thing again is concaving upwards. This graph concaves up. And because it concaves up and will always concave up, always concaves up, that means that there is no point of inflection. Excuse me. Now, let's talk about the end behaviors. Well, here, the end behaviors for this function, and I forgot to write this about increasing behaviors right here. The value of a is going to be a positive number, and of course the value of b always has to be positive, okay? The value of b always has to be positive, and in this situation the value of b has to be a number that's going to be greater than 1. This is going to result again in an exponential growth function. Now, let's look at the end behaviors. Well, in these exponential growth functions, because the left end is again, the right end, let's look at the right end. Since the right end is pointing up, as x is approaching positive infinity, your y values are unbounded and they're going upwards and they're going to approach all the way to positive infinity. In limit behavior, RE right end, RE right end, the right end is the limit as x approaches positive infinity. The function values are unbounded. So they're going to go all the way up to positive infinity. And your left end, well, is bounded. As you see right here, this thing again on the very end, on the left side and the end, again, is becoming horizontal and it's getting closer and closer to the x-axis, which is the equation y is equal to 0. This line, y is equal to 0, actually happens to be a horizontal asymptote. So the left end behavior of this function is bounded by this horizontal asymptote. And therefore, as the x values decrease without bound, approach negative infinity, the y values are bounded by this horizontal asymptote and are simply going to get closer to 0 every single time. That correlates again mathematically because since this number is going to be a positive number greater than 0, all right, raising it to a power of x is simply going to make it more positive, okay, or still more positive. So if I have the example 3 to the second power to the x value, all I'm doing to the number 3 is multiplying the number 2 to it. So I can multiply it 1 time, 2 times, 3 times, 4 times. And if I get negative numbers, which again make this exponent negative, which is simply going to get the reciprocal of this, instead of multiplying it by 2, on the negative side, I'm dividing it by 2. So 3 divided by 2, 3 divided by 4, 3 divided by 8, and so on and so on. It's still going to be a positive number. There's no way that this expression right here ends up ever equaling to a number less than 0. It's always going to end up being positive. So we're bounded by this horizontal line. So using limit notation in order to describe the left end of this exponential function using limit notation, we would write that the limit of f of x as x approaches negative infinity is going to equal to the horizontal asymptote, which is 0. Okay, now let's look at an exponential decay. An exponential decay function is going to result in a function that is obviously going to decay. So it's decreasing from left to right. The notation for such a function, again, it looks the same way. We still have the notation of f of x is equal to a times b to the x power. But the difference here is that the value of a is still going to be a positive number, but, and here's the key thing, is that the value of b is going to be a number that's going to be less than 1. So if this value of b is less than 1, then this is going to result in exponential decay. The value of a is still going to be the y-intercept. So this number right here, let me get my highlighter. This number right here is where I'm crossing the y-axis. So that point right there would be 0 and whatever that value of a is. This function is always decreasing, so just like as before, there is no local extrema. And the range for this, well, just like the previous example, the range for this are going to be the y values greater than 0. We didn't write it over here, but that's going to have the exact same range. This function up here has the exact same range. All your y values have to be better than 0. The concavity of this thing is still increasing, okay? The concavity is still, again, going upwards. It always concaves up. And because it always concaves up, there is no point of inflection. Which means that your rate of change, your average rate of change, your arc, is increasing from left to right. So I figure out the arc, the rate of change between, let's say, these 2 points. That number is going to be smaller than the rate of change between those 2 points. Okay? The rate of change is always increasing from left to right. So this point right here is going to have a smaller rate of change at this point right there. And then again, this point will have a bigger rate of change than the previous one, and this rate of change will be bigger, and so on and so on. So the rate of changes are always going to be increasing when you move from left to right. And the same thing's going to be true up here. I didn't write it, but let me just write it now. Our rate of change is increasing since it is always concaving up. Now let's talk about the end behaviors. Well, the end behaviors here are going to correlate again to the left and right end. Well, this time around, because the graph is going downwards, the left end is going to be the end that it's unbounded. So as x is approaching negative infinity, the y values are unbounded and they're going to go upwards towards positive infinity. And the right end this time is the end that's bounded, so it gets flipped around. Now in exponential decay, so that means that the y values are bounded by the horizontal isotope, which again is this, the y-axis. This is our horizontal isotope, which is the equation y is equal to 0. So using limit notations, the left end limit notation would be that the limit as x approaches negative infinity of f of x equals infinity, and the right end using the limit notation is described by saying that the limit of f of x as x approaches positive infinity equals to the horizontal isotope of 0. So it just simply gets switched around. Now, another thing that this has in common is that if you look at the two pictures, you'll notice again that an exponential decay is simply the reflection of an exponential growth function across the y-axis. I'm simply flipping this function up here across the y-axis, meaning that I'm resulting in a horizontal shift. So I'm multiplying this value by a negative number. So I can come up with a different equation. If I have the value of b greater than 1, then the equation would look like this: a times b to the negative x power. So if I make this value of b always be a number greater than 1, and I see that this exponent right here is negative, then this is going to result in an exponential decay, and the function will go downwards, resulting in a horizontal reflection of this function up there. So where the left end is unbounded and the right end will be bounded. Let's look at some transformations now. Now, explicitly for exponential functions, the transformation to shift things horizontally left and right, that notation is going to be again to our x values. Now recall that with horizontal translations, the opposite is occurring as the notation is indicating. So subtracting h from the value of x is not going to shift things to the right, to the left, but shift them instead to the right side, h number of units. And if I'm adding, that's going to shift things to the left side. Now vertical translations correlate again exactly like as they're noted, plus k on the outside, not as the part of the exponent, but out here, that's going to shift the graph up or down that number of units. Now, since these exponential functions have a horizontal isotope on one end, the horizontal isotope is also going to shift as a result. So here, the horizontal isotope will be at y is equal to k, and over here, it will be y equals to negative k because of that vertical shift. Okay. Now, reflections. Well, we're going to talk about focusing on reflections today, all right? And focusing on particularly this reflection, a reflection across the x-axis, which is a vertical reflection. So a vertical reflection. That is going to change the range from 0 to infinity to negative infinity to 0 because the graph is now going to be below the the horizontal isotope. And as long as there's no vertical shift, the horizontal isotope is still going to be at y is equal to 0. So instead of the range, the y value is going from 0 to infinity and going upwards. Because of the negative sign, this is going to flip it upside down across the x-axis, so a vertical translation, and the graph is going to be below the horizontal isotope. So your range will go from negative infinity to 0. Now, we've already discussed on the previous page a horizontal reflection because a horizontal reflection is just simply an exponential decay function. The function just goes downwards instead of going upwards from left to right. And that is referred to as an exponential decay. Now, again, we're assuming that the value of b here is going to be a positive number, all right? But this right here would just simply reflect it again horizontally, regardless of what this value of b normally is. But if the value of b is a number greater than 0, then the graph positive, greater than 1, greater than 1, then it'd be again an exponential decay. And then you have your vertical shrink. So vertical shrink, again, this value right here corresponds again to the y-intercept. And again, this is just a general form of the value or the expression, the equation of the exponential function. And then with our horizontal shrink and stretch or horizontal dilation, that value that we're multiplying, and I hate to using the letter A, but A times X looks like that. Now recall again, just like with horizontal translations, a horizontal dilation again is doing the opposite. So right here, we're not really multiplying the value by A, we're dividing by A, which is equivalency of multiplying by the reciprocal of whatever this number is, A right here. So our X values, and this is a typo, this should be B to the X. This is going to, again, do the opposite and end up with, and simply multiply it by the reciprocal of A, which is, again, like I mentioned earlier, the equivalency of dividing by A. So here we are really dividing by A. Let's now focus on graphing the vertical reflection of an exponential growth and an exponential decay function, okay? Now, in this example right here, because this value is greater than 1, highlighter, here we go. Because this value is greater than 1 and our exponent, again, is a positive x, then this is an example of an exponential growth function. And this exponential growth function will look like this. Let me zoom out a little bit and let me draw it over here. F of x is equal to positive 3 times 2 to the x power will look like this. We will cross the y-axis at 0, 3, and the graph will simply just move upwards by a factor of 2. So every x value, every time we increase by one x value, the y value is going to be 2 times as big. So this point right there would be at 1, 6, and then multiplying this x value by 2 would be at 212, and then so on, okay? All my y values are simply increasing, starting off at 3, they're increasing by 2. So 3 times 2 is 6, 6 times 2 is 12, and so on, okay? So this is your exponential growth function. Now, by having a negative sign right here, all we're going to do is simply reflect this exponential growth function. And the graph to this equation here will simply be a reflection. So instead of crossing the x-axis at 0, 3, we will cross the x-axis at 0, negative 3. And instead of, again, going upwards like this, the graph is going to go downwards because it's going to be a reflection. So the graph of f of x will look like this. Oops, I missed the y-intercept. So it will look like this. Now, this is still considered an exponential growth function because of this part right there, okay? This part right there with a positive x, again, is an example still of an exponential growth function. The only difference is that since we're multiplying our y-intercept, our a value with a negative 3, it simply reflects it across the x-axis. And because of this, the graph of this exponential growth function is actually decreasing. So even though we are decreasing, which is kind of counterintuitive because we're saying that we're growing, it's decreasing, the limit behaviors are still the same. The left end limit, or the left end behavior of this function, so in other words, as x approaches negative infinity, the left end is still, again, going towards the horizontal asymptote. So it's still equaling to 0. And the right end of this function is still unbounded, but because we're reflecting it across the x-axis, a vertical reflection, instead of going towards positive infinity, it's now simply going towards negative infinity. But this is still an example of an exponential growth function. It's just been flipped upside down because of this negative sign right there. So this is the only thing that changes. Instead of going up towards positive infinity, it's now going down towards negative infinity. And of course, the graph of this thing, the graph of f of x is decreasing. And because it's an exponential growth function, the concavity has also changed. The concavity is now concaving downwards, and our rate of change is decreasing, okay? And you'll notice again, if you look at this function here, in this situation, our graph is increasing, but the rate of change is also increasing. So for any exponential growth function, the direction of the graph and the concavity are always moving in the same direction. The graph is increasing and the rate of change, again, is also increasing. Those values are getting bigger and bigger, every single time. Now, let's look at a reflection of an exponential decay function. Now, with this number right here, again, being positive, I'm sorry, bigger than 1, and our exponent being a negative value, negative x, this is an example of an exponential decay function. Now, the only difference between this one and let's graph it over here on the side. And let me do it red this time. F of x is equal to positive 3 volts h. H of x is equal to positive 2 times 3 to the x power to the negative x power is that this one would be above the x-axis. So with this number right here being a number bigger than 1 and this being a negative exponent, the graph will look like this. It goes downward, it's decaying. Where we're crossing the y-axis at 0, 2, and for every x value, we're dividing by 3. So for every x value, every time we increase the x value by 1, we're just dividing the number by 3 every single time. So this would be 2, well, x is equal to 1, and the y value would be 2/3. And right here, let me do a table instead because I'm not going to be able to plot these, okay? So let me put the table over here. So at 0, 2, when x is equal to 1, the y value would be 2/3. And when x is equal to 2, I'm going to divide the previous answer again by 3. So that'll be 2/9, and then so on, okay? So the y values are decreasing that way, which means that if I go the opposite direction, let me go the opposite direction. So if I go to -1 to the left and go this direction, instead of dividing by 3, I would multiply by 3, and this number right here would be 6. So at -1, the y value would be 6. Okay? So it behaves again in the opposite way. So let's look at the reflection of this. Well, the reflection of this is simply going to put this graph below the x-axis, so below our vertical asymptote. So the graph of this function would cross the y-axis at 0, -2, not 3, -2. And all your y values would just simply be the opposite. At -1, the y value would be -6. At 0, your y value would be -2. And -1 would be -2/3. And at -2 would be -2/9. Okay, now look at the end behaviors though, all right? Similar to the function on the this one over here, the one on the right side, this red one right here, the end behaviors are doing the same thing. Because this is an exponential decay function, the right side of the function is approaching the vertical asymptote, which again is 0 since we haven't shifted. And the left side is still unbounded. Let me zoom in. The left side of the function is still unbounded, but this time it's going towards negative infinity instead of positive infinity. So this is the left end behavior. This is your right end behavior. And it's very similar to this one over here. Because this is again an exponential decay function, the right end of the function, the end behavior on the right end again is going towards the horizontal asymptote. And the left end is still unbounded, but because this one is above the x-axis, your left end is going towards positive infinity, while your right end is going towards negative infinity, simply because it's upside down, okay? But the behaviors, again, is the same. The left is unbounded, and the right is bounded by the horizontal asymptote. So, and because this is an exponential decay function, this exponential decay function, the graph of this exponential decay function is increasing, which again is kind of intuitive, but because we have a reflection. So the graph of h is increasing, but because it's an exponential decay function, the rate of change is doing the opposite. Your rate of change is going to decrease because it's concaving downwards, okay? And if you compare it over here, the opposite is occurring. This graph is decreasing, but your rate of change is increasing because it's concaving upwards. So the behaviors of the of the direction of the graph and its concavity are always going to be opposites, and they're always going to be doing the opposite thing when it's an exponential decay function. And well, if it's an exponential growth function, the graph, the direction of the graph and the concavity are always going to be the same. So right here, this one on the left side is decreasing and the rate of change is decreasing because it's concaving downwards. Right here, the graph is increasing, and since it's concaving up, the rate of change is also increasing as well. Okay. So again, some very important characteristics about the reflection of an exponential growth and an exponential decay function. Let's now look at more examples of identifying some key characteristics of these rational functions and, of course, their end behavior. So let's look at this example right here, okay? Now, what I always want to focus on in order to determine if I have an exponential growth and exponential decay is determine again that this number inside the parentheses, again, the base, is a number that's greater than 1, okay? If it's greater than 1, then I can automatically focus on the exponent. And if this exponent is positive, then this is going to be an exponential growth function, okay? So here we have an exponential growth function that is above the vertical asymptote because our y-intercept is a positive 4. So the graph of this function will look like this. We'll cross the y-axis at 4, and the graph is going to move upwards, okay? Now, in order to graph this function, as you'll be required to do in your assignment, I just simply have to multiply this value of 4 with the common ratio and see what that value is going to be. So 4 times 3 over 2, that is equal to 6. So I'll just simply plot the point at 1, 6. And of course, 0, 4. I'll plot the first I'll plot the point 0, 4. Then I'll plot the point 1, 6, and the graph will look like this. Okay. Now, key characteristics about this. Well, first of all, the range of this function, since it's an exponential growth that's above the horizontal asymptote, the range will be all of the y values from 0 to infinity. The range is, for any of these exponential functions, the range is always going to be all real numbers. So we're not going to focus on that because the answer is never going to change on that. But our range here would be, again, from 0 to infinity. Now, how is this graph behaving? Well, this graph, because it's an exponential growth function, the graph that's above the x-axis, the graph is increasing, and the rate of change is also increasing since it's concaving upwards. And what about the limit behaviors? Well, the limit behavior of this function, let's discuss the left end first. The left end behavior is that as x approaches negative infinity, the y values of this function are approaching the horizontal asymptote. And the right end behavior is unbounded, so the right end is going towards positive infinity. So there you have the key characteristics to this function for f. Let's now look at the second example. For this example, don't automatically assume just because this is a positive x that this is going to be another exponential growth function. You have to first verify that this number right here, the base, the common ratio, is a number greater than 1. Since 2 over 3 is not a number greater than 1, then in order to avoid any mistakes about an exponential growth or exponential decay function is to get the reciprocal of this. So simply flipping it over, 3 over 2, that makes this number bigger than 1. And because this number is bigger than 1, that would mean by our exponential rules that this exponent is going to become a negative x. So this is the function that we're looking at. And now with this value being a number greater than 1 and the exponent being negative, this is an example of an exponential decay function. So let's see what the graph of an exponential decay function is. Well, an exponential decay function, the right end is always approaching the horizontal asymptote, okay? And that's what this graph will look like. But since we have a negative value for the value of a, we're multiplying again our y-intercept by a negative sign. This is going to be a reflection of this graph. So the graph is going to look like this. But a key thing to remember that for an exponential decay compared to an exponential growth function, the right end is going to be the bounded side on an exponential decay. And with the negative sign here, our y-intercept will be 0, -7, and the graph will move upwards right there, okay? Now, in order to plot this on your homework assignment, if you have to plot this, the way we would plot this is that we would be multiplying again our value by 3/2 to figure out what the point would be on the right, okay? So to figure out what this point is, when x is equal to 1, I'm simply going to get -7. I make myself an x and y value table. So now at 7, the y value would be negative, at 0, the y value would be -7. But when x is equal to 1, I'm simply going to multiply by that quantity right there. Okay, so multiplying again, -7 with 3/2, that's going to end up becoming 21, -21/2, which is 10.5, -10.5. Okay. Oh, no, sorry. Sorry, I'm using the wrong one. We should be multiplying by this one right here. Okay. So I should be multiplying -7. So that would be -14/3. Okay. Now, since you won't be able to plot that point, then what you can do is just simply plot a point that's going to be on the opposite side by, again, getting the reciprocal of this. And with the negative sign, look at what the y value is when x is equal to -1. So if I want to use -1, okay, I would multiply by this on the left side. And that's how we're going to figure out this point over here. So -7 times 3/2, that's going to end up equaling to 21/2. So I put those backwards. So 21/2, which there, that makes sense, is -10.5. And yeah, that makes sense right there. So when x is equal to -1, -10.5 would be the point that I would plot. So let's look at some characteristics about this, okay? Now, even though this is an exponential decay, the graph of this exponential decay excuse me, the graph of the function is increasing and your rate of change is decreasing. And I know it's kind of intuitive to think that we have an exponential decay that's increasing, but the only reason it's increasing is because we've reflected it across the x-axis. But our rate of change is decreasing because it is concaving downwards. And again, that's always going to be true about the exponential decay. Whether it's above the x-axis or below the x-axis, the graph is going to be moving in one direction and its rate of change will be doing the opposite thing, okay? Now, let's discuss the end behaviors. Well, because it's an exponential decay, the left-hand side is going to be the unbounded side. So it's going to be approaching infinity. And since for this specific function, this specific function is below the x-axis, the infinity that the left end is approaching is -infinity. So this is your left end behavior. And your right end behavior is going to be the bounded side. So as x approaches positive infinity, the right end is going to be bounded and it'll be approaching whatever the horizontal isotope is. And for this specific example, that horizontal isotope is 0. Let's look at another example. Excuse me. Let's now look at example C. So again, just because this here again is positive doesn't mean it's going to be an exponential growth. We have to verify that this number is greater than 1. Well, 2 over 3 is 0.6. That number is not greater than 1. So what we're going to do to the function g is get the reciprocal to our base. So it becomes 3 over 2. And that changes the exponent to negative x. So with this being a number, with the base being a number bigger than 1 and our exponent being negative, this is another example of an exponential decay function. But this time, our y-intercept is going to be positive 5, so we're going to be crossing the y-axis at 0, 5. And the graph will go simply downwards. Now, instead of trying to figure out what the point that we're crossing over here, what the y value is at positive 1, it'll be easier to figure out what the y value is at negative 1 by multiplying 5 with 3 over 5. And then we can plot that point right there along with the y-intercept, and we can get, again, the exponential decay. This point over here on the assignment will be harder to plot because you'll need an integer in order to plot it, because you won't be able to plot fractions. So the graph will look like this, okay? Well, what are the key characteristics about this graph? Well, again, our y-intercept is 0, 5. The graph of g is decreasing, okay, which is again correlating to the fact that it's a exponential decay, and the rate of change is increasing because it's concaving upwards. Now, what about the end behaviors? Well, our end behavior, again, since this is again an exponential decay, the left end is unbounded. And the right end is bounded. So with the left end being unbounded, that means that the y values of the function are approaching an infinity. And in this case, it's going to approach positive infinity since it's above the horizontal isotope. And since the right end is bounded, the right end is going to be bounded by the horizontal isotope. Let me fix this. This should be g. So this is going to be 0. The horizontal isotope is 0 because we have not shifted it up or down. The only way we can shift it up and down again is if we were adding some quantity k right there, and then I would shift the horizontal isotope k units up and k units down. Okay. And let's just do one more, and let's change this example right here. Let's change example number 2, and let's say that this is negative x, okay? So let f of x equal to 2 of 4 over 5 to the negative x. Now, again, don't automatically assume just because our exponent is going to be negative that this is going to be an exponential decay function. You have to verify that this base is a number greater than 5. I'm sorry, greater than 1, greater than 1. Since 4 over 5 is not greater than 1, then what we're going to do is simply get the reciprocal of our base, 5 over 4, and as a result, that's going to change the exponent from a negative x to a positive x. So now, with this being a number greater than 1, now we can rely on the exponent to determine if this is going to be an exponential growth and an exponential decay. So with this being, again, that value there, then this is going to be an exponential growth function. So the graph will look like this. We would cross the y-axis at 0, 2, and the graph will go upwards. So as you can see, this graph is concaving up, or the graph increases while the rate of change also increases. Because this is an exponential growth function, the left end is bounded. Meaning that the y values of this function are approaching 0, and the right end is unbounded. Meaning that the right end is going to approach infinity. And the infinity that we approach depends again on whether we have a reflection or not. In this case, we don't have a reflection across the horizontal isotope or above the horizontal isotope, so the right end is going to be pointing towards positive infinity. Okay, and again, that's the opposite to functions that are exponential decays. In exponential decay, the right end is going to be the side that's bounded, and the left end is going to be unbounded, just like in these last two previous examples. Okay, exponential decay. So the left end is unbounded, as you see right here. The left end is unbounded, and the right end, again, is going towards 0. Okay, we'll stop with those examples, and that concludes our notes for section 3.4, right? 3.4? I'm lost now. I'm sorry, 2.4, I don't know 3. 2.4, 2.3. 2.3 exponential functions, okay? So that concludes our notes on section 2, on topic 2.3 exponential functions. If you have any questions, please send me a message through email or on Parent Square. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.